Okay, good morning, good afternoon, everyone, and welcome to BioMass Canada Cluster webinar series. Happy New Year, and I wish everyone had safe and relaxing holidays and fully energized to tackle different aspects of bioeconomy in Canada in 2021. My name is Mahmoud Evadian. I'm a research associate at the University of British Columbia working on biomass, bioenergy, and biofuel logistics and supply chain with Biomass and Bioenergy Research Group. And today we will have the third webinar from this series. And as you see that the focus of this webinar series is on de-risking and commoditizing underutilized biomass resources, specifically agricultural biomass, to facilitate the evolving Canadian bioeconomy. I'd like to give a very short background on Biomass Canada cluster. So this cluster is led by the Biofuel Net Canada network with financial support from Agriculture and Agri-Foods Canada's Agri-Science program. And also we have contribution from industrial partners for each project. The overall goal is to enhance the contribution of Canadian agriculture into the growing Canadian bioeconomy by using agricultural biomass for the production of low carbon intensive bioenergy, biofuels, and also other bio-based products. So in total, we have 10 activities, basically projects, and each project is trying to develop or improve technologies for the production, processing, and also distributing feedstock from agricultural biomass. Just a few housekeeping items. So perhaps if you have been in the previous webinars, so we record each webinar, and at the end of the webinar, we post both a presentation slide, and also a copy of the recording on Biomass Canada website. If you go to the website, click on the webinars, you can see the list of all of the webinars and also presentation recording. And also for the future webinars, you can find the registration link if you are interested to attend the future webinars. Also, we have two boxes on the webinar screen. One of them is Q&A. So please put your question in Q&A. So that makes the job easy for me to find your question and then ask this question from the speakers. And also we have a chat box, and I encourage everyone to put your name, affiliation, so at least we have a sense of social networking in this platform. Okay, so with that, I'd like to introduce the speakers today. Today we have two presentations from the same research group directed by Dr. Lope Tapil. He is a professor of biological engineering at the Department of Chemical and Biological Engineering at the University of Saskatchewan. His main area of research and interests are in bioprocess engineering, value-added engineering, bioenergy, and post-harvest handling of crops. He also has been conducting research and development projects related to value-added processing of agricultural products, including storage, drying, and cooling, and physical properties of agriculture and biological materials. So Dr. Tabel is going to present first, and then in the second presentation, we have Stepan Valdez. He actually completed his master program a few weeks ago. So he's from the same department working with Dr. Tabil, and his thesis focused on the microwave torrefaction and densification of oat hulls for heat and power generation. And his current activities, and I think that's going to be the focus of his PhD program on techno-economics and life cycle assessment of Canadian biomass plants for bioenergy production. He poses a keen interest in agribusiness, agriculture, and food industry. So, Dr. Tabil, I just share the screen, stop the screen, and then you can start your presentation. We are looking forward to that.
Okay. It says host disabled
Okay, yeah,
participant.
just give me a, yeah, I should give you the, okay, now you should be able to share your screen.
Okay. So good morning, everyone. Welcome to my presentation and Happy New Year. Um, this is timely because we haven't started our classes uh, here yet at the University of Saskatchewan. So the first part of our presentation today will be on pre-processing and pelleting of agricultural crop residues and some examples herein. I would like to acknowledge my co-authors, Kwong Dao, Esteban Valdez, Payman Alizade, Ono Ono Ologo, as well as Obiora Ago. My collaborators are Duncan Cree of the College of Engineering of University of Saskatchewan, Tim Demonsu, and Eddie or Edmond Mupondwa of Agriculture and Agri-Food Canada, Saskatoon Research and Development Center here in the campus of University of Saskatchewan. So I would like to acknowledge first the funding from the from Agriculture Canada under the Canadian Agricultural Partnership Program and Biomass Cluster Holder, Biofuel Net Canada. Our industry partners include Floating Gardens, Inc., Mystic Management Limited, Middle Lake Tribal Council, Richardson Milling. I see that Dan Charbonneau is here this morning, and SAS Power. So the goals of this particular project of ours are to support the agricultural growers at Canadian Northern Latitude by extending their growing season through supply of locally sourced biomass feedstocks for combined heat and power generation. The second is to improve market opportunities for biomass, bioenergy, and bioproducts, benefiting agricultural producers across Canada, including the northern regions, and develop environmentally sustainable technologies and byproducts for the economy, and contribute to the lowering of greenhouse gas emissions. Now, the specific objectives of the project covered in my part of the presentation are to investigate how various processing and pretreatment options influence the physical properties and chemical composition of lignocellulosic biomass, and give examples of this, and determine how pretreatment affects biomass densification and subsequent conversion to bioenergy and bioproducts. So first off is the first pretreatment that we are looking at is microbial pretreatment, and the feedstock we're looking at are the uh, uh, two um, feedstocks, camellia straw and switchgrass. And we ground them into three different manner using knife mill, a chopper, and a simulated tub grinder. And then afterwards, the materials were subjected to sterilization and incubation using Tramitis versicolor fungi. And we incubated them and then separated and then oven dried and subject to further size reduction. And then after that, we did some pelleting and characterization of the product. So the results after pelletizing was that if you see here, sorry about the crowded table here, but if you see the pelletized product here, it's the the treated one, microbially pre-treated one versus the untreated one. And so you will see from the appearance, it's darker, the microbially pre-treated one, indicating that it is denser and higher in tensile strength. Tensile strength is a way of for us to determine or to indicate the durability of our pelletized product. So unit density, dimensional stability, and tensile strength, all these pellet properties improve significantly as a result of the pre-treatment, microbial pre-treatment using Trametes versicolor. Two strains were tested, the M40 and the 52J. And we were able to do some optimization for our microbial pre-treatment. So for example, if you want to optimize with tensile strength, which is a good indication of pellet durability, is that we can pelletize, or we can do the microbial pretreatment at 88% moisture, 25 degrees Celsius, and 40 days. So if you will see that a lot of this microbial pretreatment study had a longer pretreatment time. So this long pretreatment time is an issue and can be combined with on-farm storage to solve this issue, and some engineering design here in order to sort of make this a low-cost process. And the heating value, the HHP of the pellets after the pre-treatment, as you will see here in this column, is that the values of the higher heating values of the pellets of pre-treated as well as raw biomass were within 94 to 100% of the raw biomass. So therefore, the heating value of the pellets were not much affected by microbial pre-treatment. In the switchgrass case, we can see that there is a potential, or there is the combined effect of both camelina and switchgrass have a very promising potential for pellet production and for ethanol production as well. So we did some analysis of the potential sugar yield for camelina, and it was found at 64%, or 374 grams of monomeric sugar, which is a good index for ethanol production. Another treatment that we are looking at in terms of pre-treating the biomass is ultrasonic pre-treatment, and how it affects pelleting of camelina straw, where we're looking up at ultrasonic technology to sort of aid in microbial pre-treatment, for example. And we, in this particular work we did with camelina straw, right? So we sonicated the water and ground camelina straw, and then subjected it to chemical composition analysis. And you will see that the sonication time, the one in red, is a longer sonication time of 50 minutes. And of course, if you sonicate longer, the cellulose increase, and the lignin, the acid insoluble lignin decreased. And if you look at the structure, the SEM photo of this sonicated camelina straw, you will see that there is fragmentation and cavitation with respect to the length of sonication time. Shown in these slides are the pellets of untreated and ultrasonic treated camelina straw pellets. And you will see that there is an improvement as well as, better durability index and better tensile strength was achieved for ultrasonicate or sonicated camelina straw pellets. Now, another pre-treatment that we have looked at is microwave torrefaction of switchgrass and camelina straw. And in this study, after the torrefaction, we used HD or high density polyethylene, which is recycled or coming from the waste, and use the HDPE as a binder, right? So the purpose of which is to manufacture biofuel pellets for this purpose, a combination of torrefied and bound or HDPE for pelletizing. So this is the procedure that we had. Either the camelina was or switchgrass was top ground or hammer milled, and they were torrefied at between 200 to 300 degrees Celsius. And after torrefaction, they were ground and then subjected to pelletizing. And you will see here, this slide shows us the previous work on our wheat and barley densification or torrefaction and pelletizing. And with an increase in higher heating value as a result of torrefaction, as well as the addition of HDPE. Now, for the camelina and switchgrass, and you will see here that we haven't analyzed the other results yet, but for camelina and switchgrass, the biochar mix addition, higher temperature and longer time increase the ash content and decrease the moisture content of the torrefied product. This slide shows to us a decrease in solid yield with temperature increase and with time increase for both camelina straw and switchgrass. So work on this particular is still going on, and analysis of the results are still going on. And then we have also completed the microwave torrefaction work of oat hull, which was just which was just defended by Esteban before Christmas. And we are working with Richardson Milling on this particular experiment, wherein we use microwave technology to torrefy oat hull at different temperatures. And as you will see here, so we have the oat hull material here, and we torrefied them at three temperatures, 225, 255, and 285 degrees Celsius. So can the microwave torrefaction can significantly benefit the fuel properties of our biomass, as you will see in the increase in carbon content with respect to the temperature used in torrefaction. And in terms of grinding energy used, we have seen a 86%, 64 to 86% energy reduction in grinding, and of course lower moisture absorption, and of course lower hygroscopicity. And And you will see also here the hemicellulose, cellulose, and lignin content, and the energy or calorific value of the biomass as resulting from the torrefaction process. And we did pelletize the torrefied oat hull. And from this work, we can say that the torrefaction at 255 degrees Celsius was, I think, a good option here. This curve here showing to us that the tensile strength was very good for this particular temperature. And we also tested lignosulfonate, 5%, 10%, also sawdust in the process. And so at high torrefaction levels, tensile strength and pellet durability were negatively impacted by the treatment. And the use of lignosulfonate as binder decreased the calorific value of moderate and severely torrefied pellets. High density or high dye temperature can be had or should be put into your pelletizing equipment so that we can utilize or we can successfully pelletize the product. So just as a summary, microbial pretreatment could significantly boost the physical quality of camelina straw and switchgrass pellets while maintaining the energy content of the material. And sugar yield from acid hydrolysis of pelletized material is promising and suggesting a possible pathway into the bioethanol production from these pellets. The ultrasonic pretreatment of camelina straw improve its pellet quality and percentage of cellulose content, because somehow the ultrasonication delignified the biomass. So it can be applied as a supplementary pretreatment approach to enhance cellulosic ethanol production. And microwave torrefaction of biomass biochar mix has shown significant treatment technique and efficient treatment technique with plastic waste blend using densification process. So thus we have high quality fuel pellets for biomass energy. And lastly, microwave torrefaction of oat hull increased the pellet strength at moderate torrefaction level. So we have found that at 255 degrees Celsius of torrefaction temperature was the optimal in this process. So that is all my my presentation this morning. I would welcome any question that you may have.
Okay, thank you very much, Lope. It was a very informative presentation. We have to keep in mind that we say agriculture biomass is underutilized, and the reason it is mainly the quality. So this pre-processing and pre-treatment that Lope explained in his presentation on are possible pathways to produce a commodity from agriculture biomass. So with that, we can start with the question. I think we have 10 minutes for Q&A. We already have actually 3 questions, Lope, for you. And as usual, we have good question from Mario. We have the same question from her in the past webinar. So she's asking, what are the reasons for pelletization and pre-treatment of ag biomass? What value do they add?
Okay, so the pre-treatment option is in order to increase the efficiency of utilization. So it's either to have better utilization in the biochemical biochemical pathway or a better utilization in the thermochemical pathway. So for example, if you use torrefaction, you have a better product that is higher in energy and low in, of course, low in absorption or moisture absorption, which will be better for, as fuel for thermochemical type conversions such as heat and power. And for pelletizing, I think the thing here is that biomass is produced in areas where the plant or the biorefinery is far away. And even if the biorefinery is closer to the area of production, still we need some transportation for this biomass. And pelletizing the biomass will, of course, increase the efficiency of transportation.
Okay, great, thank you. The second question from Mario is, what do you see as the primary applications and uses of the pelletized ag biomass?
One direct benefit or one utilization pathway is, of course, combined heat and power production. And if you have this kind of plant, it can benefit from pelletized biomass. The pelletized biomass come in as pellets, and they are gonna be slightly ground when they are fed into the combined heat and power production, for combined heat and power production. And we have seen in the first two pre-treatments that we have looked at, particularly biological pre-treatment or microbial pre-treatment and ultrasonication, that they can increase the production of sugars or saccharification if you go into the bioethanol pathway.
Okay, thank you. Just adding to Lopez's comment, we should keep in mind that Denmark is a great example of using agriculture biomass for heat and power generation, and they have been using agriculture biomass since 1990. And now we have a smaller scale and also large scale facility that they are using agriculture biomass for heat and power generation. So we already have a good example of using agriculture biomass for bioenergy production. Okay, we can move to this, the next question. Lope, the next question is, so Mark is saying that thank you very much for the presentation. How long did this research project take? I think it is still undergoing, right?
It is still undergoing. For example, the ultrasonication is still under, all of them except for the microwave torrefaction of oat hull.
Okay. And the next question is, what was the percentage of the mixed biomass biochar in the torrefaction process?
And I just want to see the details here. Obiora, are you there? 10, 15, and 25% that we have looked at. 10%, 15%, and 25% biochar that we have looked at. We mixed it with the ground or particle size reduced biomass, and then we subject it to torrefaction.
Okay, great. And I guess we can move to the next presentation, but if you have further question for Lope, you can type your question here, and if you have more time at the end of the presentation, we can go back to the question for Dr. Lopez. Thank you very much, Lope.
Yeah, you're welcome.
Saban, the floor is yours.
Thank you, thank you. So Dr. Lop, could you stop sharing your screen, please?
Yeah.
Thank you.
And how do I do this?
It's maybe located on the top center of the screen.
Yeah, there is a button. It said stop sharing. It should be a red button.
Okay, thank you.
Yeah.
Sorry.
No, it's fine.
All right. Good morning, everyone. Thank you for taking the time to being here. My name is Esteban Valdez. Today, I'll be presenting my master degree thesis project. Part of the project was the techno-economic analysis of outputs. Techno-economic analysis of outputs and torrefaction on for the testing plant. I would like to thank my graduate committee members, Dr. Loptaville, Dr. Edmund Mukondwa, Dr. Tim Dunoxu, Dr. Dukan Ki, and Dr. Hadi Moased. I would also like to acknowledge the government of Canada under the Canadian Agricultural Partnership or BioMass cluster holder, Biofield Net Canada, and our research partners, Richardson Milling, Brigham and Howland Microbiotechnology, Agriculture and Agri-Food Canada, and Ritz Feed and Biofuel Canada. Let's start. So the goal statement of the project is to convert agricultural waste into value-added products for the production of biofuels in a responsible and renewable way. Moreover, we want to contribute towards the climate change solution while sustaining economic development in the province as we transition from fossil fuels. For the project overview, we have to determine the techno-economics of the microwave torrefaction pellet plant using outholes as the primary feedstock in the province of Saskatchewan. Moreover, we have to determine the plant capital cost, the operation cost, size and location, and do financial analysis. So first of all, here's a short description of what microwave torrefaction is. So it's basically a thermochemical process where biomass is heated to a temperature range of 200 to 300 degrees Celsius. And this treatment is gonna benefit the biomass fuel properties. So with the temperature range of 255 degrees Celsius, which is moderate torrefaction, we can increase the heating value of our outholes from 16.8 to 20.7 megajoules. We can see a reduction in the moisture absorption of our pellets. From the raw pellets of outholes, we have 22% moisture absorption. And with the treated pellets, we have 12% moisture absorption. This is really important because the more water that we have in the pellet is going to lower the heating value eventually. And also it's going to increase the transportation cost because we have to move the weight of the water as well. Moreover, we have a better biomass grindability. We're decreasing the grinding energy consumption from 80% energy reduction with this treatment. This is because we have a disruption in the lignocellulosic matrix. We're removing the hemicellulose, which is giving support to the structural wall of the cell. And by removing the hemicellulose, we're also kind of freeing the lignin. Lignin is a natural binder, which we can use in densification process to increase the tensile strength. So we also have an increase in tensile strength in almost 50% with the use of torrefaction. Tensile strength, as Dr. Lop explained, is a way of estimating the durability of the pellets. Is kind of the hardness of the pellet. So if we have a really soft pellet, when we are transporting the or pellets, we can have some dust formation, and this can be something dangerous because we have risk of explosions. I would like to comment that for the microwave torrefaction process, we have our main product, which is the mass, which is 70% mass yield. But we also have a couple of other byproducts, which is the liquid fraction and the gas fraction. From the liquid fraction, we have mainly water. We have a lot of chemicals as well. We have over 400 different chemical compounds, which are mainly classified into phenols, which gives the flavor and the smell of smoke. We have carbonyls, which gives the color, the brown coloration that we can see here. We have some acids, mostly acetic acid, and we have some tars, which I will explain later on. We also have the gas fraction, which is mainly carbon dioxide. It's also composed of carbon monoxide, and we have some other smaller gases as hydrogen. For the techno-economic analysis, well, this is a methodology to analyze technical engineering design and economic evaluation of a process, product, or service. So for this project, we evaluated the construction of a small-scale torrefaction plant, incorporating costs, benefits, uncertainties, and timeframes. So this analysis was underdone using this software, the Super Pro Design software. Now, for our techno-economic analysis, we decided to explore two paths. The first one is the commercialization of torrefied pellets only. And for path number 2, we have, again, the commercialization of torrefied pellets and the production of liquid smoke. So from the liquid yield, we can type of filtrate or liquids and in order to reutilize it as liquid smoke. This is a really valuable product in the food industry because it gives the smoky flavor and color to the food products. So if you ever purchase it, smoke turkey breast or smoke cheese, it's really a high chance that they are formulated with these smokes. The reason for this is because they are much cheaper than traditional smoking houses, and we have a higher homogeneity of the product. So we have our process flow diagram for path 1. As you can see here, we have the transportation of the hulls from the source of the feed, in this case a mill, to our plant. And so we have a feedstock silo. From the feedstock silo, we have to move the product to our torrefaction system. After the torrefaction system, we're going to have 2 streams. The top one is condensable and non-condensable gases. These gases, we can separate them in a condenser. So basically, we're separating the liquid yield, which we can later use for heat production. And we have the non-condensable phase, which are mostly carbon monoxide and the dioxide, as I was mentioning, which we can recirculate into the system to maintain an inert environment. This is important because if we have oxygen in our system, we're going to have a higher loss in mass. And remember, we want to keep or get the most pellets possible. After, on the bottom one, as I mentioned, is the mass flow. After torrefaction, we have to cool down our mass because it's really dry, it's really hot, and it can self-ignite. So we have to cool it down. After cooling down, we have to grind it prior pelletization. Here it's important that we have that reduction in grinding because it's energy savings. After the grinding, we take our mass to the pelleting system. From the pellet mill, we have to cool down the pellets again because they may self-ignite. From the cooling, we have a screen mainly to remove some fine particles or undensified pellets which can generate dust. So after removing those, we can transport the pellets to our trailers or pellet bin storage silos. So for the process flow diagram, path 2 is exactly the same path. However, here on the liquid fraction, we added some equipment to filtrate and remove the heavy tars. So we have some sedimentation tanks. These tars will eventually condense after 10 to 15 days. And it's important to remove them because they have some hazardous compounds like benzene or toluene. And as we know, that's cancer risk for the humans. And after the sedimentation tanks, we have filtration unit is a membrane to furthermore eliminate any risk of these stars being present in the smoke. We have our capital cost analysis. This was underdone with consultation of private companies. So we have a research agreement with Frick and Mahallan from Germany. So they provide us the estimation cost and the size, estimated size for this type of technology. And as we can see, it's really, really expensive technology, almost $4 million for the equipment. Again, it's for part 1 and part 2. So we have the equipment purchase cost, which is everything related to the pellet mill, the grinder, the augers, the silos. And for sure, we have installation costs, piping, instrumentation, insulation, and how much will it be for the building. And how much will it be for engineering of the building and the plant and for the constructor's fee. As we can see at the bottom, we have a total investment of $10 million for part 1 and $30 million for part 2. As mentioned before, compared to conventional torrefaction, we have conventional torrefaction here and traditional wood pellet plant. The proposed technology of microwave presents a higher capital cost due to the really high equipment cost of the microwave system. As we can see, it's almost twice expensive for a microwave system compared to traditional ones. We have also the power demand. So we have a breakdown of electricity consumption to produce 1 ton of torrefied pellets. And we have an estimation of almost $40 to produce 1 ton of torrefied pellets. From this, the most expensive source of energy consumption is for sure the microwave system, which utilizes more than 50% of the electricity consumed. After we have the pellet mill, and then we have a general load consumption, which is mainly the kilovolt amperes. So as we know, when using electricity, we have to pay for the kilowatt hours and for the kilovolt amperes. So it's kind of a glass of pint. I would like to explain this like this. So if you have a glass of beer, the beer is the kilowatt hours and the kVA is the foam at the top. So even though you're not actually drinking it, you have to pay for them. So for economic evaluation report, we have the summary for part 1. As mentioned before, we have a capital investment of $10 million. We have an operation cost of $4.6 million, which includes the operation cost, the raw material cost, the labor cost, utilities on transportation of the feedstock. And then we have our revenues, how much money we're getting from selling the torrefied pellets. From these two, we can see our gross margin, which is 2.18%. We can see a payback time in almost 11 years. And we have a negative net present value. And I will explain the meaning of this negative sign here. And now we have the summary for part 2. We have a higher capital investment due to the extra equipment for the microfiltration of the liquid. We have a higher operation cost as well because we have to add the membrane use, but we have a higher revenues from both products. So from those extra revenues, we can see an increase in the gross margin in almost 50%. We have a return on investment of 66%, and we have a payback time in 1.5 years of the plant. We can see a net present value, a positive net present value of $42 million. So for the financial analysis, one tool that we could commonly utilize is the net present value, which is the difference between the present or actual value of cash inflows and the present value of cash outflows over a period of time. So it's a way of taking the future cash flows and discounting those back to the present day. So you can decide how much will you pay for that project or that service. So if we have a positive NPV, it's indicating a profit to the company. If we have a negative NPV, it's indicating a net loss. So the reason to do this type of analysis is because the money in the present day is worth more than the same amount in the future. and it's due to inflation and due to earnings from alternative investment that could have been made during the time frame of X project. Now, we can set some discount rates for the net present value as well. So these rates or percentage is based on expected return from other projects with similar risk levels, or the cost for borrowing the money from for the project from the bank. And for example, if a company can avoid a project that is expected to return 10% per year if the financing cost is more than 10%. Or if we have another project that is going to have a higher return. So it's a way of choosing our investments. So here is a really simple exercise that I made for the plant. So for part one, we have our fixed price, which can vary for sure from $10 to $20. We have a different percentage for the discount rate of the net present value from 7 to 20%. And we have a different selling price of the pellets. We have from $110 to $150 per ton. So the average is 130 based on previous research. So this is kind of the average selling price for our pellets. And here we can see that even though that we have a really low fixed price, a really low net present value percentage, and really average selling price of the price, the net present value is still negative. So this is a sign that the project will generate losses eventually. We have to hire like really high pellet selling prices in order to have a positive profit. For the part two, we have the selling of the pellets and the selling of the liquid smoke. Again, is the same exercise as the first part, but we can see a positive net present values in all of them, even though we have a really high feedstock price, a really high net present value discount rate, and a really low torrefied pellet selling price. We still have a positive factor, well, which is telling us that it's going to be a good investment if we do it. So for summary, we have that industrial microwave systems present major advantages in terms of being compact. They are up to 1/5 the size of the traditional heating equipment. They are faster. They are more controllable because we can stop them anytime that we want. And they're than conventional heating methods. And this is due to a faster processing time. Microwave torrefaction costs can be reduced. However, a higher capital investment is needed, which reduces the project's growth margin and profitability without the use of other byproducts as the liquid smoke. From the refinement of microwave torrefaction, condensable gases into liquid smoke can increase the gross margin, which could become the basis for providing a business case for these type of systems. And last, we have incorporating the recent equipment cost data from microwave systems and pellet plant components as possible to have an accurate analysis. Thank you very much.
Okay, thanks a lot, Esteban, for detailed information on your techno-economic analysis. We have two questions from Maria. She's asking about mainly the capital cost. She's saying that the capital cost for what size of plant and also the assumption of the price of pellet that you consider in the analysis of your internal rate of return.
Oh, great. So the size of the plant is 4.5 tons per hour of torrefied pellets.
Okay, and then you mentioned you showed some data on the net present value. So I saw that you assume different price of pellet and also liquid smoke. Can you sort of mention those price again?
Yes, so the assumed price of the pellets is $130. And from the net present value, we kind of play with them from 110 to 150. And for the price of liquid smoke, I put it $1 for kilogram. I consulted with companies that utilize this liquid smoke, and they told me that the price range is from $2 up to $10 for 1 kilo. So it's, I think it's justifiable to put those prices there.
Okay. When you say price of pellet, is it the price at the gate of the pellet plant or the price delivered to the end user?
Oh, yes, this is important. It's the price at the pellet gate, yes.
Oh, okay. So it's not include the transportation, the storage handling is not included. Okay.
No, it's not included yet.
Okay. And one more question from me. So the liquid smoke, what are the, do we have any existing application for liquid smoke?
Oh, yes, for sure. Within the food industry, we have, they utilize it a lot for providing a smoke flavor to the food products. So for hams or cheeses or bacon, it's really commonly used.
Okay, okay. So we have one technical question. It's about microwave treatment. So Hamid Reza is asking, are microwave treatment reactors capable of working in a continuous process or only should be operated in a batch process?
Very good question. And it should be a continuous process. The reason why is because if we stop the microwave from working, we're going to damage the magnetron. So in order to have a longer life of the magnetron, we have to have a continuous process.
Okay, great. Okay. And I don't see any more questions, but Lope, I have a question for you regarding the, so we are talking about commoditizing agriculture biomass, and you and also Stepan talk about different pathways again for pre-treatment, pre-processing. Which of these pre-processing and pre-treatment you think is going to be more promising in the near future to make agriculture biomass like a commodity, or at least a product that can be sold in different markets, similar to wood pellet for heat and power generation?
We're looking at torrefaction and this microwave technology. Also looking at, whether we can use conventional torrefaction, heating for torrefaction. That way, this can be used for combined heat and power type of applications. We know that torrefied product has a much higher heating values, and of course, with that, I would say that the price, the pellet costs should look at, because the one that Esteban has looked at was more into the wood pellet type cost with a lower heating value. So if you have a heating value, let's say 24, 25 gigajoules per kilogram, I think that is sort of a better, a better selling point, and also a higher price for the pellets.
Okay, great, thank you. Stepan, there is another question for you. So what is the yield of the liquid smoke as a percentage of the total liquid portion?
So with the temperature of 255 degrees Celsius, we have a yield of 20%.
Okay, 20%. Okay, thanks. One more question. Let's see, I think it's, yeah. So liquid smoke is made from wood by companies like Red Arrow. Can you comment on the different like compositional flavor economic between the liquid smoke made from wood and liquid smoke made from agricultural residue?
Oh, yes, for sure. And as I mentioned before, there's a price range from $2 to $10 and from liquid smoke. So based on that flavor profile, we have like a sweet flavors or sour flavors or bitter flavors. So depending on the type of flavor is going to be the price of the smoke. So this type of smoke is going to have a low economic value because the type of the feedstock. So I don't know if that answers the question.
Okay, thanks. Well, again, Johnson, if you have more questions, you can follow up with the Stepan. Johnson is one of our PhD students at UBC. So we have two more questions. I guess we have still time to ask this question from you and Lope. The next question is, how do you estimate the selling price of liquid smoke? Does type of feedstock affect the quality of food grade liquid smoke?
Oh yes, so the estimation was based on inquiries with the private companies. So I contacted a Canadian private company and they were able to tell me the price of how much they were paying. I was able to contact one of the biggest companies in Mexico as well, and they mentioned the price range as well. And this is how I base the selling price of the smoke. And yes, depending on the feedstock, it's going to affect the quality of the food grade. Not the food grade, but the flavor profile. The food grade is going to be safe because we have to do the pre-treatment first to remove the cancerogenous compounds.
Okay, thanks. And the next one, what percentage of the 20%, I guess you mentioned the 20% portion.
Yes.
What percent of the 20% would be the tar portion?
So for tar portion, we have between 3 and 4%. So that tar is not a waste. We can use it to generate heat for like oil. It's really heavy, so it's about 26 to 28 megajoules per kilo. So yes, it's another product that we have.
Okay, thanks. I don't see any more questions, but again, I asked the participants, again, you can find the information on the website, the BioMass Canada cluster. I'm sure you can find Lope and also Sapan on the University of Saskatchewan website. I'm sure it's going to be easy to find them on the website. So if you have any follow-up question, please feel free to contact them. So with that, I would like to close this session. And I just want to mention that the next webinar is going to be on January 21st, same time, same like Thursday, 11 to 12 p.m. Eastern time. And that's going to be about the application of thermochemical and hydrothermal pretreatment in the production of fuel pellets using agriculture waste. So Lope, Sapan, I really appreciate taking the time to share some of information on the activities you are leading in BioMass Canada cluster. And again, I thank all of the participants to attend and also being engaged in the discussion by asking the question. Thank you very much and have a good day.
Thank you very much.
Bye.
Bye-bye.